period 2 element, I saw some people write and that conveys a bit of a misunderstanding. Or sometimes people do write that. But for our purposes, I don't want to see that. The reason is it's primarily the valence electrons that are involved in chemical bonding. And it's primarily the valence electrons that are shared between atoms. So the molecular orbitals that can be built from the 1s electrons, those are core orbitals. And really, a given orbital is, that electron is very close to one atom, and it doesn't really interact with the other atom at all. So there's no bond formation. I know I'm mixing nomenclature now, but we're really not interested in orbitals that arise from the core orbitals. We're interested in orbitals that arise from the valence orbitals. So there becomes a bit of a funny thing. If we're talking about H2, well, for hydrogen, the valence electron is the 1s, the valence, right? So we would speak about the 1 sigma G, and in fact, this 1 sigma G for hydrogen is formed from the 1s, and it really, if you now use the valence bond term bond, valence bond theory term bond, that really is involved in bonding. However, for lithium 2, that's period 2, the first molecular orbital that is involved in gluing the atoms together, thinking of bonds, is built from the 2s and not from the 1s. So get it clear. A number of people, when talking about period 2 atoms, were talking about 1s's. This isn't incorrect, but in the context of our discussions, we've not made reference to those, and we talked about the 1 sigmas for period 2 as coming from the 2s's. So those couple of things. Any questions on those ideas? Yeah.
If you get a chance, could you go over the nomenclature for like benzene, like when it was like the A2U, or there was a different.
Sure.
There was a different nomenclature.
So for benzene, there are 4 orbitals that are formed from the PZ electrons, or the PZ orbitals, and they have a nomenclature. I'm just going to give it to you, but I'm not going to tell you where it comes from. But it comes from the topic of symmetry, which is one we didn't have time for. I can say just a little bit though. These highest and lowest energies have orbitals that are given the names A and B, and numbers 1 and 2, and then the symmetry is given G and U. So that's fine, they're non-degenerate, right? The middle 2 are degenerate, so I often indicate that with 2 lines. Let me make sure I get this correct. Ooh, see, I already got it wrong. It's the A2U and the B2G. So, and that's actually quite obvious. So if you think of the A2, the parity is obvious. So the A2U, we have actually a bunch of these in a row, right? 6 of them. Plus, 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 plus. Oh, they actually should be not in a row, but
In the top view or something.
you know, like this. So I'm not even gonna try, okay? Because it's three-dimensional, but it is actually, if you reflect through the center of through the origin, the wave function changes sign. You have to think three-dimensionally, and the pictures in the book are two-dimensional pictures looking down from above, and they'll confuse you. It will look like it's G, that's because it's a two-dimensional representation. So that's U and that's G, and then this is E1G and E2U. Okay. And you can figure out the U and the G if you think about it closely. E is used for orbitals that are degenerate, comes out of symmetry theory, and then we just have the numbering 1, 2. But did that answer your question, Joe?
Yes, thank you.
Okay. Another thing I wanted to mention, I asked you to draw matrices for the the matrix or the secular determinant for some big molecules like anthracene.
Very difficult.
In principle, difficult. A lot of people put down matrices or secular determinants, but they didn't draw the molecules and number the atoms. And it turns out, whenever you have a molecule with a bridge, and those are the bridges, in order to draw the matrix correctly, you have to first draw the molecule and number it. Each row in the matrix corresponds to a particular atom. And there are certain elements in the matrix that depend on how you number the atom. And let me make it clearer with, I'm trying to make it really simple one here. So here's a molecule with 6 carbons and 1 bridge. It may not be stable, I don't know if you find it in real life, okay, but there it is. So let's say that we were going to draw the secular determinant for the pi system here. I'm really not worried. I guess we need double bonds. Anyway, let's not worry about that part. If it's, I'll go ahead and draw the secular determinant. Now I'm going to number these 1, 2. Let's just say this sort of, it makes sense. This is row 1, this is column 1, and the rows and columns, the first row corresponds to carbon 1. So now all along the diagonal, we will have alpha minus e's. If you write this with alpha minus e's and betas, that's fine. If you write it with x's and 1's, that's fine. The principle is the same. Oh, that's all we got. Okay, so cool. So along the, no, we need 2 more, I'm saying. 1, 2, 3, 4, 5, 6. Okay. Now, this is going to correspond to atom 2. Remember, beta, this entry is beta if the corresponding atoms share a bond, and it's 0 if they do not share a bond. Atoms 1 and 2 share a bond. 1 and 3, they don't share a bond, right? 2 and 3 do share a bond. 1 and 4 don't share a bond. 2 and 4 don't share a bond. 3 and 4 do. 1 and 5 don't. 2 and 5 do, though, because of this bridge. And then 3 and 5 don't. 4 and 5 do. Hold it. Okay, so it's 2 and 5 that do. So if this is 2 and this is 5, that's the beta. Yeah, there we go. Okay. And then lastly, 6 and 1, they actually share a bond. But 6 and 2 don't. 6 and 3 don't. 6 and 4 don't. 6 and 5 do. So that's, oh, it's beta. So that's how you get it, right? Now, suppose that I just decided to number my atoms differently. And I decided I was going to start here. This matrix now has to change. The diagonal elements are fine. These are fine. But there's no longer a, if you look here, this is saying that atoms 5 and 2 share a bond, but they don't. So now we have to do that, right? And same thing here. On the other hand, this is saying 1 and 4 share a bond. Well, here's 1 and here's 4. Oops. No, here's 4. That's got to be a beta. Down 4 and 1, that has to be a beta 2. So if you draw the matrix without this, I can't possibly evaluate it whether it's correct or incorrect. It doesn't have enough meaning. So I made this remark in some of your questions. Now there was one other thing that came up frequently, but Atkins and I have a disagreement. So he and I have to have a conversation, and I'll come back to that later. He might be wrong, and I might be wrong. So we'll just have some. Because I just noticed this like 15 minutes ago, so I don't want to even talk about it. Cool. So, brainwash, that's gone. Where were we? So we were talking about spectroscopy, and we gotten into infrared spectroscopy last time. Vibration and rotation are both involved. So I want to continue with that conversation. We devised an expression for the energies last time of the transitions. Those were basic energies. So I'm going to start there, and then I want to go and add some correction terms and describe those. Then I'll talk about how we relate the energies to the transitions. And then after that are a couple of odds and ends. And we'll generalize to polyatomics just briefly. So that's kind of the order of the day. But let me begin with the energies. If you remember, we said that the energy now depends on two quantum numbers, V and J, and it would be now these are in energy units, not wave number units. So I remind you that we defined S of V and J as the energy divided by HC. And so for the rest of this is like backtracking. I just want to make sure we're all on board. So from now on, I'm going to talk about the wave number units because it's more convenient. But that gives us then H goes away, and I'm going to use that, and I can use that because the wave number is equal to nu itself divided by the speed of light. Okay, this would be reciprocal in reciprocal or centimeters. This would actually be in hertz per second. So that's what we're going to use. So that's our expression for S, which we would call the vibrational rotational term. It's not an energy, it's a term. Now, this is actually corresponds to an approximation. We call that approximation the rigid rotor harmonic oscillator approximation. So the rigid rotor part is here. Remember that B is defined as one definition of it. And the point is that I itself is, for a diatomic, 1/2 mu r squared, right? No, it's mu r squared. It's mu r squared. So we're assuming there's a fixed bond length. Rigid rotor, it can't stretch, it can't compress, it isn't. Okay, so our approximation is the rigid rotor approximation. The harmonic, I'll remind you the harmonic oscillator approximation is that if that's the bond length and this is the energy, the energy can be described, the vibrational energy can be described by the energy levels of our harmonic oscillator. Well, that's fine. It works pretty well. And that gives us the energies we're used to. Yeah. There's the 0 point energy, and here's the first excited state, and so forth. That's fine, but real molecules have potential energy surfaces like that. And they match the harmonic oscillator pretty well toward the bottom, but they'll break, right? The bonds break. So that's an approximation as well. Okay. So how do we go beyond the rigid rotor harmonic oscillator approximation? We have to add correction terms to the energy. Now, one of those you've met before. Can anybody remember what it would be? You met it?
Distortion.
When we talked about rotation.
The centrifugal.
Centrifugal distortion, exactly. So as the molecule rotates, the bond stretches. So we can correct that, and I want to write this straighter. I am challenged in this respect. So let me just start over.
Oh my god. I don't know the distortion for
I'm going to write it this way. So this is the term for centrifugal distortion. Remind you.
I have to do this series.
That's the centrifugal distortion constant. And notice this is the square of this. That's a pattern you're going to see repeated. So that corrects for centrifugal distortion. What about the fact that your molecule is not really harmonic? It's distorted from that. The next correction is for anharmonicity. This distortion from being harmonic. So this is for anharmonicity. And this is called the anharmonicity constant. Now, it's written kind of in an odd fashion, right? Here there's one constant, it's nu. Here there's one constant, it's p. Here there's one constant, it's really minus d, to tell you the truth. The constant's d, but the correction is negative, and the correction here is negative. But the correction is actually xe times nu. This is purely a historical artifact. So truly, the anharmonic correction is xe nu times v plus a half. But for historical reasons, this was written as some correction times nu. You can think of it as one thing together. Okay? So this is the anharmonic correction. There are actual higher anharmonic corrections too, times v plus a half cubed, and 1 times v plus a half fourth, and so forth. So this is, more precisely speaking, the first anharmonic correction, but there are more. Okay. So we got those, and you'll see there's one more that we're going to talk about in this class, and that is this one. This is called the vibration rotation coupling constant.
It's a long equation.
Or rather, this is the vibrational rotational coupling, is the way I really should put it. And this is the vibration rotation coupling constant. Okay. And it turns out that the coupling of vibration and rotation generally decrease the energy, therefore the constant is defined as positive and we use a negative sign. It's a convention. Same thing here. The anharmonicity generally decreases the energy. We choose to define the constant as positive and then we need a negative sign. Now, how do we understand this vibrational rotational coupling? Well, if you think about it, if you have centrifugal distortion and the bond stretches, then the bond will have a different force constant at that. The effective force constant is now changed, and therefore the vibrational energy has also changed. This is now increased. So there's an interaction between vibration and rotation, and that's captured this way. So I want to talk about a couple of these in greater detail. You can just memorize these, but I want to talk about a little bit about this one right here and its source, the enharmonic part. And I want to talk about it partly because it's fun, partly because it introduces you to a model that's used pretty often to model a molecule that can actually break. And this was introduced in one of the labs for those who are taking the lab. It's called the Morse potential. So, we know that the potential energy surface of a real diatomic molecule is going to look something like this. It will break. This allows the breakage to be modeled. Probably the simplest mathematical form you could give that captures this shape, although it might not exactly capture the shape for any particular molecule, was devised. Clever people did it, I don't know when, years ago. It looks like that, and that looks kind of complicated. Let's define some things. So the dE, you'll remember, is the well depth, right? The depth of the well. So dE is the well depth. And if we convert to units of wave number units, we speak of dE with a squiggle on top, and now to get energy we have to multiply that hc. Okay, so this is why the hc dE is here. That just converts to units of energy. What about the rest? We have a definition also for A. So A is defined as Now, MeE is the effective mass, and for practical purposes, it's the same thing as mu, the reduced mass, same definition. But the text uses effective mass, and so I'll stick there. Times omega squared all to the 1/2. That looks very complicated, right? But that's the definition. And one nice thing is that you can set up the time independent Schrödinger equation for this potential energy, and it can be solved analytically. It has solutions. I'll tell you what they are here. But before I do that, I want to do some sense making with this. And let's first of all see what V of 0 is going to be. Well, if I plug in 0 for x, I get e to the 0, which is 1. 1 minus 1 is 0. Okay. So V of 0 is 0. So, I guess it would be, we're going to call this 0 right here. That's x equals 0, and this is going to be V equals 0. Next, let's think about what happens if x gets very small. Put that over here, x, if it gets very small, what happens to V? If x is less than 0, let's think about that. So this becomes e to the minus x, so if x is negative, this is positive here. And as x gets large and negative, this becomes a very large number. It will overwhelm the 1. So you have a very large negative number, but then it's squared. So it becomes a very large number, positive, times this. That's what happens when x gets negative, this goes up. You can only compress so far, and then that's as far as you can compress. And it's very energetic. It takes a lot of energy to compress that bond a lot. So all I can say is the energy goes way up. Now what happens what is the limit of V of x as x approaches infinity? Well, let's think about that. As x approaches infinity, this becomes 0, right? E to the negative infinity is 1 over e to the infinity. This is 0. So this is just 1 squared is 1. So we just have HCDE, which is, so if this is 0 and this is HCDE, right, that's the well depth. So everything fits this picture pretty well. But there's more. Let's think about this for a second. Remember that omega for a harmonic oscillator is the force constant divided by mu, we said, but mu is the same thing as the effective mass. So if we square this and we multiply by m, what we're left with is just the force constant. And I left off a 2. I see now. That's defined with the 2 in the denominator. Let's rewrite this without the squiggle to keep things simple. Okay. So this becomes 2 times dE. Now dE has units of energy because I don't have the tilde on top. So A is the square root of the force constant divided by the well depth. Now, I will tell you something that you would have to check out. Suppose you take the second derivative of V with respect to x squared, and you evaluate it at x equals 0. Remember that the second derivative is the curvature, so we're talking about the curvature when we're at the minimum. And you will find out, if you plug everything in, I'm not going to bore you with that, what you end up with is a force constant. In other words, the Morse potential is built so as to give you high energy when you compress a lot, zero energy when you're at the equilibrium bond length. It's set up to reproduce the well depth, which is the thing that can be measured, and it's set up to reproduce the force constant, which can be gotten from a measurement of the frequency here. So this may not match any particular potential energy surface exactly, but it gets a lot of the aspects right. It's also not a harmonic oscillator, right? I mean, if I draw my picture of my harmonic oscillator, it's going to look like that. It's just the region where it doesn't do so well. Now, it turns out if you plug this potential in to the time-independent Schrödinger equation, I'll just plug it in, the solutions are known exactly. And the solutions are, the energy depends on a quantum number V, and that turns out to be or if we were to convert to the vibrational term, just divide everything by HC. This is the vibrational term. And what you see is that we have the anharmonicity that we talked about before built into the levels. Now, it's interesting to compare visually the levels. Suppose, and with red lines, I draw the lines for the energy levels of our harmonic oscillator. They just keep going up. You know, this is fictitious. You can't have that energy, the molecule's broken, but that's what a harmonic oscillator would give you. What about this other one? Well, they start out, the Morse potential in black gives you energy levels like this. At the bottom, it's going to be very close to the harmonic oscillator. But because of that negative term, the larger V, the more the Morse begins to depart from the harmonic oscillator, and the Morse gets closer together and it never goes above the dissociation limit. So it's kind of nice in that way. Questions? Yeah.
I see that you drew those lines slanted.
That's because I am challenged in several ways.
Okay, I just wanted to make sure that it was.
Would you like me to correct them?
No, it's fine.
They're all horizontal. I'm more about talking than drawing. That's just the way I happen to be. Okay? Other people are the reverse, you know?
I was just wondering.
But I'm more about talking than drawing. So there we go. Another interesting thing that can be shown, it's not even hard to show. For the Morse potential, there's a relationship between the well depth, the vibrational constant, and the unharmonic constant. And it's this. Couple of things. First of all, notice this and this have been written in units of reciprocal centimeters, weight number units. X has no units. But anyway, if you measure dE and you measure nu, then you can calculate X. Now this is strictly true only for Morse potential, so you should put an approximate here, an approximation sign, and then you have something that's, you know, descriptive of any molecule. Good. If you don't have a high accuracy measurement, but you do have nu and dE, then you can approximate Xe from that. It's not hard to show, it's pretty easy to show. Questions? So that's kind of, I introduced this because it's such a nice model. I wanted you to see how Into the model, you build the well depth, you build the vibrational frequency, and you build, well, basically those two things, right? And the effective mass. Okay. So cool. So that's the source of this one. Now, as I said, this is only the first n-harmonic constant. We can add higher order terms. These are all second order terms. This is second order in J, this is second order in V, this is first order in J and V, so it's second order overall. If we go to third order terms, we'll get, for example, Q. This would be the second n-harmonic constant right here. And if you read spectroscopic papers in spectroscopy that report high precision data, they'll have out to sixth order sometimes, you know. So, let me see. Okay. Now I want to show you a slide for a second. To finish our discussion of the energy corrections. This has all been about the energy corrections.
But right now he's like transitioning.
Okay, so we just got done talking about this and we took it apart. I want to provide a generalization to kind of make sense of all these terms. Notice that each of these terms has a physical, it can be understood in terms of the physical properties, centrifugal distortion, n-harmonicity, and so forth. One can also think of these purely mathematically as power series. So I want to show you the mathematical way to think about it. To remind you that you can expand a function as a power series, as f of x, right? If it's a function of two variables, the power series is more complicated. So here you have some coefficient times x, 1, 0, some coefficient times y, 0, 1, coefficient times x squared, y squared, or xy. So, in thinking in those terms, are the first and second order terms. So for us, this is the first vibrational term, here's the first rotational term. There's the n-harmonicity, and there's the centrifugal distortion, and finally there's the vibrational rotational coupling. And so with that, you can easily see how to expand a series. Okay, so now I want to set that aside and talk about how to determine all of these spectroscopic constants from data. So regardless of whether we're talking about absorption spectroscopy or scattering, which is Raman spectroscopy, a molecule's absorbing light, a molecule is absorbing energy or giving off energy, so it's absorbing a photon or perhaps scattering a photon. So if absorption is the process, this is what's happening, you know, some photons coming along and getting absorbed. So the energy of the photon, of course, is equal to the energy of the transition here. Now, when we think about this, it's going to be easier to use spectroscopic units, so we'll use wave number. So I'm going to talk in terms of the photon has some wave number. And instead of talking about E, I'm going to talk about S, final, and S, initial. So then conservation of energy says so that's it. So we just have to use this formula and think about what the selection rules are. So we use the formula and we think about our selection rules. So for IR spectroscopy, delta V is plus or minus 1, delta J is 0 sometimes, but more often it's not observed, or plus or minus 1. Now, for absorption spectroscopy, at normal temperatures for most molecules, almost all the molecules begin in the ground vibrational state. Just the Boltzmann distribution says that. So consequently, we're really only going to be considering delta V is equal to plus 1. And then delta J can be equal to plus 1. That will be for the R branch, or minus 1, and that's for the P branch. So we'll talk about those separately, the R and the P branch. Okay. Now, a word to the wise, I guess. It's easy to get confused with this nu here, because we use this nu to describe the frequency of absorbed radiation, but we also use it to describe the vibrational constant. So we're going to have to keep them separate. I'll make it easy though. Let's talk about the observed news for, that's the frequency of the photon absorbed for the R branch. That's going to be SF minus SI. So SI will be I'm going to do this explicitly in the rigid rotor harmonic oscillator approximation. Once we've done that, we'll see the principles and we can easily expand it to include the corrections. Higher order. So this will be so that's the wave number in the initial state, in the final state. What is it? So this V is the same thing, but notice in the final state, it's the V we had in the initial state plus 1 because of this change. So I put the 1 here, 1/2 becomes 3/2. Now in the R branch, delta J is plus 1, so J becomes J plus 1, and J plus 1 becomes J plus 2. Then we simply have to take the difference, and that difference is going to give me the frequency of the light. So this minus this just gives me nu. Now let's think about what this becomes. Multiply this out. multiply this out. So when I take the difference, the j squareds cancel. 3j minus j is 2j. 2 minus 0 is 2. So those are the frequencies that we should observe. Depends on the value of j, of course. Questions? Good. So let's do the same thing then for the P branch. For the P branch, delta j is -1. The initial state is the same. Now what about the final state? The vibrational part doesn't change. Delta V is still +1. This should be 3/2. So that doesn't change. What about this? Well, j becomes j minus 1. So j is j minus 1, j plus 1 becomes j. So let's multiply this out. So when we do this, so the vibrational part is just like before. What about the next part? Well, this becomes j squared minus j. This becomes j squared plus j. Minus j is minus 2j. So this becomes now there is a third branch, of course. Third branch is the Q branch, defined by delta j equals 0. It's not observed in most molecules, but it will be in some. I'll just tell you the result you get. Q branch is, the frequency for the Q branch is just nu, because since delta j is 0, the j parts will cancel out. Questions? So let's make a table. I want to predict the spectrum. So I'm going to begin by making a table, then we'll draw the spectrum. So if j is 0, then I'll start with mu r, that's going to be 2b, right? Mu plus 2b. There is no value for j equals 0 for nu p. Remember, if we think about our branches, we've got if this is v equals 0, this is v equals 1, this is j equals 0, 1, 2, 3, 0, 1, 2. Now delta j is going to be equal to -1. If I start here, I'm going to go up to here. If I start here, I'm going to go up to here. If I were going to start here, there's nothing for me to go to. If delta j is going to be -1. So the pre-branch does not include a line for j equals 0. So I just have to write that there. Now what if j is 1? Then nu p is going to be nu minus 2j. R is going to be nu plus 4j. 4b. Boy. Two nu minus 4b. Two nu plus 6b. And of course, the Q branch doesn't change. Okay? One line. So now we can draw our spectrum, and it's the way we've kind of seen things before. Let that be frequency. It could be nu R or nu P, depending on what we're talking about, or nu Q. It's just it's the frequency. So if we let this be nu, that's the frequency of the Q branch, right? So that's going to be one giant thing. That's the Q branch. For the R branch, we're going to have nu plus 2b, nu plus 4b, nu plus 6b. And so on. So this is all the R branch, and we have, and if we went on, we get the typical change in intensities that reflects the Boltzmann distribution and the degeneracy. And then over here, for the P branch, you can see the first frequency is nu minus 2b. Something like this. Now, a couple things about this. Notice that the spacing between any two peaks in the P branch or in the R branch is 2b. So you can get the same information from IR spectroscopy about B and then about bond lengths that you got from microwave spectroscopy. No difference there. That's true here. It's true over here as well. It's also true up to here. Now, if there is no Q branch, that was if there was one. If there is no Q branch, you won't see a peak. But what you will see is this distance is now equal to 4b. And notice that nu is right in the middle. So even if you don't have a Q branch, you can figure out the vibrational constant nu. It's the midpoint between the two initial peaks for the P and R branches. It's just halfway in between. Questions? Now, I need to erase a bunch of stuff. Figure out what I want to do next. Okay. What happens next if you include all those higher order corrections? This was the Ridge-Groder harmonic oscillator approximation. What happens if you include the higher order corrections? Well, all of the energies, or the two terms, they shift a little bit. And what do they become? So now we have to include all the higher order corrections, and I'm not going to even draw them in, okay? But you're going to get different solutions. Now I'm going to take you back to the lab. No, I'm going to let you see something right out of my notes.
Ooh.
I think that's better. So you're not gonna have time to write all of this down, so please focus on the principle. If you ask me later and you want my notes, I'm happy to share them with you, but I'm not gonna take the time to draw them, and I'm not gonna give you time to copy them, okay? But I can share them later if you want them. What happens if you include all of those correction terms? Here I'm thinking of the R branch. Again, S initial, S final. Notice I've got the centrifugal distortion, I've got the anharmonicity, and I've got the vibrational coupling. If you take the difference, you get this.
Thank you.
Don't copy it down, but you can just see naturally. We begin with the first two terms we had before, but now there are corrections. I can do the same thing for the P branch, and that's what I get. For the Q branch, it's this. Now this is going to start sounding like the lab to somebody. What you can do very cleverly, but I want to show you why it works, because in the lab you were just told this is true. If you define m equals j plus 1, I'm defining m for the R branch, what are you going to get? I thought I had this drawn up more slowly. I guess I didn't draw it out more slowly. Well, if you define m equals j plus 1 for the R branch, that equation up there becomes this equation. If you define m as negative j for the P branch, you get the same equation. So what? So on this next slide, I've got two colors. Now, when you substitute in those values for J and figure out what numbers you get for M for the R branch, you actually start with 1. So it goes from 1, 2, 3, and so forth. And that gives you the R branch. So you could, if you have a bunch of data, you could fit all those data to a line. That's the black line. If you do the same thing for the P branch, well, the first value you're going to get is -1, so that goes that way. You can fit all those to a line. That's the red thing. Well, since these two expressions are equivalent, and collectively you have values of m going from -4 all the way as high as you go, you could actually fit the whole thing to one line. And that would give you more accurate values for your spectroscopic constants ultimately. So, this should look very familiar, but I want to show you why it works a bit more now. So here, this is for HCl, here's the spectrum, as you've all got from the lab. There are double peaks because there are 2 isotopomers, and the taller one is for the 35Cl isotopomer. So here I'm talking only about the 35Cl. You have to assign each peak to its value of J. That's for the initial state. There they are. You can assign the M's. That's the frequency measured for the peak. Then you can fit all the data to a cubic term. So the coefficient of m cubed is minus 4dj. That's 0.00213. The coefficient of m squared is negative 0.30378, and so on. So from the fit, you can determine the spectroscopic constants. All these. You actually cannot tease apart these two because they're the coefficient, they're the constant term. And you need more information to tease them apart. Questions? So we now have talked about the basics of how we use spectroscopy to determine spectroscopic constants, and then from those, of course, we can get properties of the molecule, the bond lengths and force constants, even dipole moments for other experiments. I now want to talk about a few details. One is, how would we determine a dissociation energy from these kind of data? And the next picture shows you, you'll find this thing called the Burge-Sponer plot in your book. Let me take it apart slowly. But what this is telling us is how measurements of the vibrational transitions, how we can use those to determine the bond dissociation energy. Amazingly enough. First of all, notice that if you make a transition from V equals 0 to V equals 1, if you can measure that transition, you've gone one step up the ladder toward dissociation. If you combine that with energy from 1 to 2 and 2 to 3, you add all those up and you're going to get D0, which is the bond dissociation energy. In units of energy here and units of wave number there. So that's pretty cool. Now you're probably thinking, oh, that's nice enough, but we're told with the Boltzmann distribution, for most molecules, the signal for V1 to 2 is going to be pretty weak. That's true. But for some molecules, you can raise the temperature and access the higher transitions. They're all still delta V equals 1 transitions allowed by the selection rules. So if you can get, you probably can't get all of them, but if you can get a number of them, you can extrapolate. That's what the method's about. So what we want for the bond dissociation energy is the sum of all those red arrows. So we define this thing up there that has the funny symbol delta G V plus 1/2, V plus a half, as this way. G of V plus 1 minus G of V. That's just the length of an arrow. That's all it is. It's the length of an arrow. It's also that if you subtract out the energies of the two terms, including anharmonicity. Now remember, the anharmonicity is what causes these spacings to get closer and closer together as you approach the dissociation limit. Without anharmonicity, the spacings are the same. You never dissociate. So the clever thing to do is to plot delta V a half versus the number a half. So if V is 0, then V plus a half is a half. And the vertical distance here is that delta G of 1/2. Delta G of 3 halves and so forth. Well, let's think about what the area under the curve is. Well, let's just think about this rectangle. Okay. The width of the rectangle is 1, and the height of the rectangle is delta G of V plus a half, where V is 0. So the area is 1 times delta G, which is the same as delta G. So in principle, the area under the curve is the same as the sum of all the arrows, which is D0. So you can plot this out and get the area under the curve, and you have D0. Now in practice, the first anharmonic constant by itself does not provide a sufficient correction, and you would need second and third order anharmonicities. So the true numbers probably deviate like this. So the triangle gives you an overestimate, but still a decent estimate. So you can get a D0 this way, and that's kind of cool. The next sort of footnote I want to talk about is this. Number 2 is in your text, and number 1 is not. Number 1 I talked about in class, and number 2 I didn't. What am I talking about now, and why? These are 2 different ways to get at vibrational rotational coupling. One is the one on top. Some texts use, some spectroscopists use. Others use this. And they define a rotational constant differently for every vibrational level. And the idea is, generally, if you increase the vibrational level, the bond length, the equilibrium bond length for that vibrational level increases a little bit. Okay. So if you go from V equals Z to V equals 1, the bond length's just a little different on average. You might think during the course of vibration it would all average out, but it doesn't. And that's because the moment of inertia is proportional to r squared. Anyway, that means the effective B in a given vibrational level is defined this way, but it's going to be different for every vibrational level if you choose to do that definition. And so instead of talking about a global alpha, they talk about vibration V-dependent rotational constants. I chose not to do that. You shouldn't worry about it. If you ever have to become experts or in the field a little bit, read about it. Either way, you're getting the essence. I'm just pointing you out why the book and I are talking about different things. Questions? There's one other thing. Totally. Oh, no. Yeah, I'll finish with this today, and then I'll say a word about polyatomics on Monday before starting electronic transitions. Remember Raman spectroscopy? It applies to vibration as well as to rotation. If you remember the selection rule for rotation, it was the polarizability had to be anisotropic, right? That was the gross selection rule. You can also scatter light and thereby change your vibrational level, you know. But the gross selection rule is not a little different. The polarizability has to change still. But now it has to change during the course of vibration rather than the course of rotation. Okay, that's fine. It turns out that even homonuclear diatomics will change their polarizability as the bond gets stretched. You know, remember the polarizability. We're talking about the electron density that changes as you stretch the bond. And it becomes, the polarizability also changes. Point being, we couldn't get information, vibrational information with IR spectroscopy, which is absorption, for homonuclears. There's a selection rule, but we can for homonuclears using Raman. So here are the selection rules. Delta B is the same. Delta J is now plus or minus 2, though. So we speak of these branches, minus 2 for delta J, that's the O branch, Q branch again, plus 2 is the S branch. So notice, minus 2 is O, minus 1 is P, 0 is Q, 1 is R, 2 is S, it's just alphabetical. Now, if you remember, we have possibility of Stokes and of anti-Stokes scattering, transitions during scattering. And to remind you, if we have a set of levels here, and we start here, Stokes means we go up to, we can think of Stokes as a photon comes in, excites us to a virtual level, and then de-excites us to a V plus 1 level. And we could have started right here, actually. That's Stokes, right? No, we better leave it there. Anti-Stokes means that we excite up here and we come down minus 1. Okay. So notice that we cannot have anti-Stokes if we start here because there's no place to go to. So to get anti-Stokes spectra, you're only talking about out of the first excited vibrational state, and that's not populated much, Boltzmann distribution. So the Stokes spectra, the Stokes are always stronger than the anti-Stokes in this case. So what you're seeing are the O and P branches, O and S branches for the Stokes radiation, same story as before. But now the spacing is 4B, 4B instead of 2B. Okay. A small tail here, but it allows you to make measurements on home nucleus as well as heteronuclears. Get all the same information. Otherwise, the interpretations are the same. So we've really covered now all of rotational and vibrational spectroscopy for diatomics, which was our emphasis, to get across the points. I'm going to make a small comment about how we would extrapolate polyatomics on Monday, and then we'll begin our last topic in spectroscopy, which is electronic spectroscopy. I guess I'd better shift the date the homework is due until Monday at midnight, so I'll do that, because I think there are some questions that pertain to polyatomics, so I'll make that switch. That's it.